Hello and welcome back to Calculus 2. We are starting the topic of differential equations, and we'll spend a little bit of time learning about what differential equations are. We'll see one method for solving differential equations of certain types, and we'll see several very cool applications. But really, we'll just scratch the surface of differential equations. There are entire courses dedicated to studying just certain types of differential equations, and you'll probably go on to take some differential equations courses. But here we're really just going to get an introduction to the topic. So for today, we want to understand what differential equations are, and we'll see how to model some real-world phenomena using differential equations. So first of all, let's talk about some of the terminology involved here. A differential equation, and we can just abbreviate that as DE, is an equation that contains some unknown function, and usually for the function we'll just call it y, or sometimes we'll use y of x, but it really doesn't matter the function name. But it contains some unknown function and one or more of its derivatives. So very simplistically, a differential equation is an equation with derivatives. Just very simplistically, we could describe differential equations that way. The order of a differential equation is the order of the highest derivative. Now we're familiar with mostly first derivatives, but we could also take second derivatives like f double prime or third derivatives, really as many as we want. And if we look at the differential equation, the order is the highest derivative. So here's a few examples of differential equations. Right here are the differential equations, and we can see this first one, we have just a first derivative, so this one is order 1. Second differential equation, we also have just a first derivative. So once again, that's order 1. This differential equation involves y triple prime. That's a third derivative, so this would be called a third order differential equation. And finally, the last one here is a second order differential equation. So we have equations that contain derivatives of some function y, and sometimes notice that the differential equations have x's in them, or this one is phrased in terms of t rather than x, and but we have some unknown function y and one or more of its derivatives. We call a function a solution to the differential equation if the differential equation is satisfied when that function and the associated derivatives are substituted in. So here we have the list of solutions for the corresponding differential equations. Now, when you look at these solutions, you probably think to yourself, where in the world did these come from? Like, look at that. That's pretty complicated. So we'll understand So at this point, don't worry about understanding where these solutions came from. Just understand that we have differential equations, equations with derivatives, and then solutions are just the function itself that satisfies the differential equation. Let's take a look at one more term, and then we'll work through some examples. These solutions in the table here are called general solutions. Notice that each of them has some constant c. In fact, some of them, this third one here, has 3 constants, c1, c2, c3. So the presence of these constants tells us that these are general solutions. And if this plus c reminds you of the plus c from integration, that's good because basically, essentially, that's where these constants are coming from. And notice, when we have first order differential equations, we just have one constant. For this second order differential equation, we have 1, 2 arbitrary constants. For the third order differential equation, 1, 2, 3 arbitrary constants. All right, let's take a look at some examples. So for example 1, we want to find the general solution to this differential equation. It's a differential equation because we've got a derivative equal to something. So this is a differential equation. Let's go ahead and solve this one. So our differential equation is y prime equals cosine of x minus 1. Now notice this differential equation, we have y prime only expressed in terms of x. So how could we recover the original function? What would be the solution here? Well, the solution is the function y written in terms of x. And can you think of how to recover the function y from y prime? Well, y prime is just written here as a function of x. So if we were to integrate this function of x, we would find exactly what the original function y was. And that's exactly what we do here. We integrate cosine of x minus 1 with respect to x, and we get positive sine x minus 1 plus c. So our solution here is sine of x minus 1 plus c. This is about as simple as differential equations get. Now let's check that this is actually the correct solution. If we take the derivative here, y prime, well, this requires chain rule. We take the derivative of sine, that's cosine, of x minus 1. The derivative of x minus 1 is still 1. So we get y prime equals cosine x minus 1, which is exactly what we started with. So we know that this is the general solution to the differential equation that we were given. Now from this example, you might think, oh, differential equations, this is super easy. It's just integrating stuff. We've learned a bunch of integration techniques, and just from this example, that's all we did. In general, however, we cannot just solve a differential equation simply by integrating. In this case, all we had to do was find the antiderivative of cosine x minus 1 because y prime was just this function of x. But sometimes we can have differential equations that don't just depend on x. We could have y prime written with y's on the other side of the equation. So in general, just a simple integral will not usually solve a differential equation. For instance, look at example 2. We want to find a solution to this differential equation, y prime equals y. Now, notice that this problem says find a solution. We actually haven't seen a method for solving this yet, so we're going to sort of use our intuition and try to guess here. And later on, we'll actually see a method that analytically allows us to solve this. But right here, I think we'll get some good intuition for finding a solution to this particular differential equation. So example 2, notice the difference between example 2 and example 1. In example 2, we have y prime equals y. We've written y prime in terms of y, not in terms of x. So if we were wanting to solve example 2 like we solved example 1, then we'd find y prime by integrating everything on the other side of the equation. So let's see, y equals the integral of, well, we just have y here. So we integrate y and then with respect to x, or is that right? Or is it integrating y with respect to y? You see that we're kind of stuck here. I could solve the other example because I had y prime as a function of x. Here, y prime is written as a function of y. So I can't just integrate directly here to find a solution for this differential equation. Some other technique is required, and we will see that technique in a later section. But even if we don't know the general technique for how to solve this, do we still have some intuition that will help us here? Take a look at what this differential equation is saying. It's saying that the derivative of some function y equals the function y itself. Can you think of a function whose derivative is equal to itself? Maybe pause the video and just think for a second. Can you think of a function where you take the derivative and you just get the same function back out? Can you think of one? How about y equals e to the x? I'm going to just write this down as a guess. This is what my intuition is leading me toward. Is this a solution to the differential equation? Well, I could check it. If I look at the derivative y prime, well, the derivative of e to the x is e to the x. And e to the x is also y. So yes, indeed, y prime equals y. This solution satisfies the differential equation. So this is a valid solution. Now, how in the world do we go from this expression, which doesn't contain any logarithmic or exponential stuff that we can see, how do we go from that to get y equals e to the x? What if we didn't know about this y equals e to the x? We'd be kind of stuck. So later we'll see a general method for solving this kind of a differential equation. Now, can you think of any other solutions here? This is one solution. Can you think of more? How about y equals 2e to the x? What's the derivative of 2e to the x? Well, the derivative of 2e to the x is 2e to the x. So the derivative here, once again, is equal to itself. In fact, we could write the general solution. The general solution for this differential equation is y equals any arbitrary constant times e to the x. Once again, we didn't work through the process of analytically solving this from start to finish. We just sort of guessed because we knew of a function whose derivative equaled itself, and then we came up with the general solution just from our guess. Later on, we'll see analytically how to start here and work through the steps to get this answer rigorously. But this expression is the general solution for this differential equation.